One. Hello, this is Dave Borton, Mill City Roasters, along with
Joe Morocco from Cafe Imports.
Joe is going to get into the weeds and the woods today. He's going to discuss heat transfer. Complex subject. I always try to break it down very simplistically into conductive, convective, and ambient. So Joe, without further ado, why don't you weed into the woods?
All right, here we go. You guys ready? Okay, so heat transfer. First of all, what is heat? Heat is energy. And when you talk about heat transferring, you're talking about energy moving from one object or one material to another object or material, or if you have a particular material, how that heat moves through that material. So when we talk about a roasting machine, as you can see, we have a bunch here lined up at Mill City. We are talking about how the heat moves from the heat source, which is your burner, to the drum or the air, and finally from those mediums to your coffee.
Okay. So you've really touched on all three there.
That's right.
Conductive, convective, and ambient.
That's
all three
right.
of them. Okay,
Yeah.
good.
So the ambient heat generally is going to be the overall heat that's kind of leaking out of the system. There are some systems that use a type of ambient heat, in particular infrared heat, which is heat that is generating a type of light that they shine onto the drum. Particularly Diedrich machines use this. There are some other machines that use this as well, like for instance, the little Hookie 500 I have has an ambient burner or an infrared burner, shines heat onto the drum. But that heat is really difficult for us to quantify. It's difficult for us to control. If you have a halogen bulb heat system, that heat is also an infrared type heat. It's heat that's coming from a light source and shining onto whatever medium that it's heating. However, we kind of want to eliminate those from our conversation today because what they do is transfer their energy from that source to a conductive surface. So for instance, in a Diedrich, we have a Stronghold at Cafe Imports that uses a halogen bulb. In a Hookie 500, they shine light energy onto a metal surface, and then that metal surface or the air, that's where it turns into conductive energy. Does that make sense?
I'm with you.
So what is conductive energy? Conductive energy is the energy of touch. So if this were a big hot plate and I put my hand on it, that would be conductive energy. If I keep my hand out here and I feel energy emanating from this source to my hand, that would be the infrared or the ambient heat coming off of that. Now, infrared is one type of light beam that carries heat, one wavelength of light, so to speak. So all light energy that you see is ambient heat. It's a type of ambient heat, but infrared is a very tight band of ambient heat. So if I'm holding my hand out from a source, I may not see that source glowing, but if I'm feeling heat from it, it's still some type of light emanating off of that. It's some type of light energy, even though it's outside of my scope of being able to see it.
Okay.
Does that make sense?
Yes.
Okay, cool.
Put my hand near the stove, infrared.
Yes.
Put my hand on the stove, not only am I dumb, but I've experienced conductive energy.
That is correct.
There.
Yep, that's right.
Good.
Or if you put your hand in my hand, Dave, that's conductive energy. Okay, so the coffee that you have in the coffee roasting drum is obviously touching the drum, right? And so it's collecting energy from the drum and it's pulling that energy into itself, and then it'll take that energy and either hold on to it or it will share that energy with another coffee seed that it comes into contact with. That's your conductive energy. Where it gets kind of confusing and like really watered down is when we start talking about different kinds of metal, different kinds of material, and how they pull energy from the heat source and then displace that energy into the seeds themselves, okay? So we hear a lot of conversations in the roasting community about a cast iron drum being better than a steel drum being better than a stainless steel drum, rolled steel versus stainless steel. So I wanted to take a little bit of time and talk about energy transfer through those different kinds of materials, okay? So there are a few things to think about. One thing is that heat will transfer from the hotter unit to the cooler unit. Heat will transfer from the hotter part of a piece of metal to a cooler part of a piece of metal. Okay, this is a thermal transfer of energy from one place to another. Heat's not going to like skip over a certain place. So like if you have a drum, for instance, and there's a heat source underneath that drum, that heat isn't going to heat here and also heat back here. It's going to slowly migrate across the medium until all of the energy in that drum has somehow equalized. So heat wants to equalize. So when you talk about the drum material, there are two things that you need to consider. One is how quickly that material absorbs heat, and two is how quickly that material gives off that heat. Some materials will absorb heat and hang on to that heat and not give it away very easily. Other materials will absorb heat very, very quickly and give it away very, very quickly, okay? One type of metal that is very fast and efficient at energy absorption and transmission would be aluminum. In fact, it's so good we don't use it. It's so good that it actually might even melt if you started using it in your equipment. But if you have an aluminum pan and you set that aluminum pan on one of those electric stove coils, the aluminum pan itself will get electric stove coil style heat. It's so fast at absorbing heat and giving that heat off to the other side that it doesn't really transfer that heat across the medium of the metal. So we have to have heat transfer with a metal medium that allows for not only absorption but retention of that heat long enough so that the heat is thoroughly heated. So that's why you see stainless steel, rolled steel, and cast iron as some of the main ingredients for the metal that you see in a drum. Now, a lot of people think that cast iron is some kind of magical metal that cooks really well. And I think that this is a misnomer of how we have come to think about cookery in culinary arts. Cast iron is a very cool way to cook. It's a very cool way to cook a steak. It's very cool if you're going to sear something because it absorbs heat thoroughly. If you put a cast iron skillet down on a stove, you can come back 10 minutes later and the handle still may not even be hot because it's still working at absorbing heat. But that's really an inefficiency and not an efficiency. So with
Say that again.
So it's really
the cast iron is?
It's very slow to absorb heat, but then once that heat is in that cast iron, it's very slow to give that heat off. Okay? So in other words, it holds on to whatever energy it has for a long time, but it takes a long time for the energy to go into that material. And I want to juxtapose that from aluminum because they're almost opposites.
I can see that.
And you can measure these things. You can measure these by how many BTUs will transfer through an object in how many feet in a certain amount of time. Aluminum is very fast. Cast iron is very slow. And in the middle of that, we have our rolled steel and our stainless steels. Now, a lot of people think that rolled steel and stainless steel are not as good at cast iron for roasting purposes, and we're going to get into that a little bit. But first, I want to talk about how they absorb energy. The softer the material, the more slowly it's going to absorb energy, okay? The harder the material, the more quickly it will absorb energy. There are also reasons for the way that a certain material will absorb energy in how its molecules have been, how they have been fit together. So if they're offset molecules versus inline molecules, those molecules that are offset will have a harder time absorbing energy through that material. Whereas if they're inline molecules, like for instance aluminum, aluminum, as we know, if you bend aluminum, you cannot bend it back into the same shape. It's so inline. The molecules, once they take a different shape, you can't refix it. So that material will transfer heat very quickly. Okay, I'm getting a little in the weeds.
Woods. You're deep, deep in the woods. Come on out to the path,
Right,
Joe.
help me out. So how do these systems correlate to a roaster? Well, if you want to roast coffee, you don't only want the metal getting hot, you want the metal to give that heat away. With a cast iron drum, it's important to understand that you have to get that drum very hot, and it needs to stay hot for a long amount of time, not just until your temperature probe reads that it's a certain temperature, but really until that heat is fully emanating in that machine. Because as you roast, as you do batch after batch, your cast iron is going to absorb more and more energy. And it's kind of like getting a giant boulder to start rolling down a hill. Once it has that momentum, there is nothing that you're going to be able to do to slow that momentum down. So, in other words, you need that to have the momentum of its full rolling down the hill before you start roasting, or else one batch is going to be different from another batch, which is going to be different from another batch. That cast iron is also going to give off a lot of emanating heat, or infrared, or ambient temperature, which is going to affect your temperature probe. So on a cast iron drum, generally, you're going to see a turnaround temperature that is much more high, because there's more of that average that your temperature probe is reading coming from the metal itself. And it's also not going, like your first crack will happen at what appears to be a lower temperature. Your end temperature point is going to seem like it's a lower temperature because your coffee seeds are going to be less of the gradient of averages that your temperature probe will read. I hope that makes sense.
So what you're saying with the cast iron, there is so much energy retained within that wall that could influence the bean probe and make that end temperature seem lower than compared to another drum type.
That's right.
Okay.
Yeah, and when you make a gas adjustment on a cast iron machine, you expect to see your temperature start to ebb off. That temperature is really not going to drop for a long amount of time. It's going to take a long amount of time for that to kind of catch up with where your adjustment needs to be. That said, there are actually very, very few drums that exist that are truly made out of cast iron. So it's important to know that if there are cast iron parts within your machine, that it's probably not the drum itself. It's usually going to be the faceplate of the drum or some other components of the drum. Maybe it'll be the arms and ribs that are holding the drum together or that are spinning your coffee back and forth. The drum itself is not generally going to be that way. Now, if you go historically and look at why cast iron drums existed, it's because we didn't have MIG welding, 150 years ago, 100 years ago, 75 years ago. These are new inventions that have come along that have allowed us to work with new types of metal and make precision machines out of those. Before, if you wanted a large piece of metal, you had to cast it. And cast iron was the way that you did that. But that creates a very heavy machine and a machine that is not easily controlled with energy efficiencies, or if you're making an air or a gas adjustment, it's not going to see the change really quickly. Whereas on the inverse of that, when we go over to stainless steel is very intuitive and it can absorb heat really well. It holds on to heat very well, but it also gives its heat away very well. And if you need to cool it, it will cool in a great amount of time so that you have a lot more control over the way that you're roasting. So heat exchange through stainless steel is kind of in the middle between where cast iron is and where aluminum or copper is, which are very energy
Joe,
efficient.
an intermediate takeaway for me then is one is not superior, nor is one inferior, but we're back to the issue of you got to know your roaster.
Yeah, and so then we get into the convection side of this.
Okay.
And this is where a lot of roaster manufacturers will start to temper the type of metal that they're working with how they bring hot air into the drum or cool air into the drum, how they mitigate the way that the metal is heating. So if you have a high efficiency roaster, if you have a metal like for instance stainless steel, then you should have a lot of air control, and that air should probably be hot as it's coming into the drum. If you pull a lot of cool air into the drum on a machine that has metal that will change temperature very easily, that cool air coming into the drum will drop the temperature of not only your coffee but also the drum itself. Whereas if you have cast iron or something that really holds on to heat for a long amount of time, you really could bring in cool air and use that as almost like a buffer to help you control your heat in a better way.
A damper, so to speak.
Yeah, so you open that damper all the way up and it can bring in a lot more air that is not being heated as much so that you can control that temperature as your drum gets really, really hot.
It's helpful.
Yeah, so this creates a picture of systems, and this is the main takeaway, is whether or not you have a cast iron drum or a rolled steel drum or a stainless steel drum, or if you're roasting on a popcorn popper, or if you are roasting with a sieve and a air gun beneath it, no matter what your material is for transferring energy, it's important to understand that material, understand the way that the airflow works with that material, understand how that's affecting your temperature probe, and then control all of those things together. A stainless steel drum, a cast iron drum, a rolled steel drum, these are all fantastic materials if they're used properly. They can all take in heat, and they can all put that heat into the coffee. It's a matter of what you want to do with the other controls that you have, what you want to do with your burner to get that machine up to temperature, maintain that temperature, control that temperature to be put onto the coffee, and then also how you control your airflow to bring in either cool air or hot air or however you want to manage that. So managing the system is much more important than what material is my drum made out of. Now, it's also very important that if you are buying from a roaster manufacturer, that you know that they understand their system's usages. There are a lot of manufacturers out there that use all different material, and they have engineers that are running mathematical scenarios to see how temperature changes with different materials, different airflow, different gas settings, etc. There are some that are not, managing these systems. So it's important that you know that the system works. And we're here at Mill City, and I'm not trying to sell a Mill City machine. I don't get paid if they sell these machines. I don't get paid if they don't sell these machines. So either way, I am neutral in this, even though I'm doing the video for them. But I want you to know that these systems are awesome, and they use stainless steel in the drum. I've roasted on stainless steel drums that are not awesome and that seem to have displacement of heat all over the place. And some of the beans come out roasted and some of the beans come out under roasted and some come out burnt. It's about the system overall, not about the metal of the drum.
Okay, so on that, we've covered conductive energy, where that bean is against the drum or against another bean. You want to talk about how these systems impact convective energy.
Yeah, so convection is that energy of air, or the energy of, you can use water. It's the fluidity of energy. It's kind of similar to conduction, but instead of it being a material surface that you are in contact with, it's a fluid surface that you're in contact with. So it's at the molecular level, not just at a hard surface level. So the molecules in the air, or if you're like boiling something, the molecules of water that are coming into contact with the material that you're trying to heat will take energy from the heat source and carry that energy to the material that you're trying to cook. So in a drum, the air is usually going to be pulled across the burner set. It's going to be heated up, and then that air is going to displace that heat onto the coffee. Some of that heat is also going to be displaced onto the metal in the drum. Some of that heat is also going to be displaced onto your probe. So whatever that air that is hot comes into contact with that is cooler than it, it will give off some of its energy.
Joe, you've got the pen there for a second?
I do.
When we look at roasting here, we've got the drying phase. And here, and I'm looking for affirmation.
Yes, sir.
We've got the air on low. I want that air holding the temp in there, and most of the heat coming in would be conductive energy through the drum.
That's right.
Once we get into the caramelization, we're turning that fan up to medium, and there, my thinking is, what I want to do is use that airflow to fluidly heat the beans from one another. The beans at that point have some energy. So I'm trying to get the airflow to share that energy among the beans. Is that the correct theory?
Yes, and also it's important to understand that conductive energy is not as efficient as convective energy. Now we think about, during this stage, it's tough to think about it and say, oh, why would I want a low efficiency way of heating? Well, because we want to give time for the coffee seed to fully absorb the energy. So when we're drying the coffee or getting the coffee ready for chemical reactions, this is almost like preheating your coffee, just like you preheated your roaster. Right now you're preheating your coffee and readying it for these reactions. And then once you get to the point where you can start these reactions that are flavor creators, then you want to bump up to your high efficiency heating method. And then the material that you're using, drum-wise, will either impede this process or assist this process. Or hopefully will kind of stay neutral to the process and just create an environment in which that convective energy can do its job.
Very good. Okay, Rao talks about 75% of our roasting is convective and about 25% conductive. That figure strike you as right?
I would say that that is a very general figure for a lot of different systems, but the vast majority of heating is certainly going to be in a convective way if you have airflow moving through that drum.
Sure, and neither of these are pure. This drying phase is not purely conductive. Some convective occurs, and likewise in the caramelization phase, that's not purely convective. There's still some conductive from both the drum and bean-to-bean contact.
That's right.
Okay.
Yep.
And all of these are dependent upon you effectively using your system, regardless of drum composition, RPM, variable speed on the drum, or airflow damper systems.
That's right.
Okay, very good.
Yeah, so I'll show you one other thing here about energy transfer and heating, which is kind of fun to think about. So here you have a medium. Up here you have something that is very hot. So let's call this 1,000 degrees. Okay? Down here you have something that's cold. Let's just call this 100 degrees because that's going to keep it nice and round and to our
Ability to...
Yeah, hypothetical here. So here, let's call this 500 degrees, okay? So this is your air temperature as it comes into the drum. It's going to be very hot because it's coming off of the burners, okay? This is your bean temperature as it comes into the drum. It's going to be very cool because it's coming out of room temperature. And this is the drum because you've preheated that drum, okay? Now obviously your burners are going to be much hotter and your burners are going to be controlling all of this. But as your air comes in off of those burners, your air is actually going to displace its energy like this, okay? and your beans are going to start absorbing that energy like this. And everything is going to start neutralizing to this temperature here, okay? So if your air temperature is much higher, then it's not necessarily going to correlate that your bean temperature is going to rise too much more quickly. But it will start rising a little bit more quickly because it's going to drag, this temperature is actually going to drag your drum temperature up a bit, okay? So then you'll move the whole scale. So when you talk about different kinds of metal, different speeds of air, different ways that the air move across the burner set, it's really these three sets that are kind of in tug of war together, okay? To see how quickly this bean temperature is going to match up with whatever drum material you have, and how that air temperature and speed is going to affect all of that. Okay? It's kind of simple. It's very complex, but it's also very simple. And at the end of the day, what you have to think about is avoid like getting lost too much in like how many BTUs per square inch is my drum going to absorb and move from one place to the drum to another. You know, how many cubic feet of air is moving through at what temperature and will displace onto that metal. All of that stuff is so complex that it does not result in your understanding of the cup. So whatever system you're using, it's important to understand this system is set up in a way that it will work together. And if I have controls that I can manage and that I can understand, then I can use this system that I have to create the perfect cup of coffee for me, okay? So don't feel bad if you have a certain drum material. If somebody tells you don't ever buy a drum that has this material or only buy a drum that has this material, it's more important that it's a system, that you understand the system, that you can control the system, and at the end of the day, what's the most important thing?
Does the cup make you happy?
That's right. We're going to harp on that every single time, okay? Are you happy with your coffee? So if you can control those variables and you can create a delicious cup of coffee, then whether or not it's cast iron, stainless steel, or plastic, it doesn't really matter. What matters is you've controlled it, you understand it, and that is why I say the three main things that you need to understand to get this is know your drum, know your coffee, and know how to taste.
Simple. Nick, what do you got there in the way of questions today? Anything?
Not a whole lot of questions. A lot of people just eagerly tuning in to view you guys, hanging out.
Hear Joe's words of wisdoms from the weeds and the woods.
Okay.
That sounds good to me.
It does. It's alliterative.
Okay, if there aren't any questions, a couple of things. Joe and I are going to take a look at in December on our New Year's resolutions on roasting. That should be good. Maybe we could even get Nick on this side of the camera because he should have a very long list of New Year's resolutions on his roasting. So we look forward to that. We appreciate you tuning in. And for conductive and convective, we say goodbye.
Bye.
See you next month.